The concept of energy generation has always been a cornerstone of human progress, and throughout history, visionaries have pushed boundaries to discover new ways to power our world. One such modern-day inventor, Maxwell Chikumbutso, has introduced a device that claims to revolutionize energy production through what he describes as a microsonic energy system. This technology, rooted in principles explored by pioneers like Nikola Tesla, has ignited curiosity and controversy in equal measure. Let's unpack how it works, its scientific underpinnings, and whether it holds genuine potential to reshape our energy future. At the heart of Chikumbutso's invention lies a combination of components familiar to electrical engineering, MOSFETs and transformers. MOSFETs, or metal oxide semiconductor field effect transistors, are widely used in electronics for their ability to switch currents rapidly. In this system, they are cycled on and off at extremely high frequencies, generating pulsed electrical signals. These signals are directed into specially designed transformers, which differ from conventional ones in both structure and function. Instead of merely stepping voltage up or down, these transformers interact with the high-frequency pulses to induce current in secondary coils, even when those coils are not physically connected in a traditional sense. This process is said to generate what Chikumbutso terms frequency-amplified amperage, a method of producing usable electrical current through rapid electromagnetic interactions rather than standard voltage application. The system's efficiency hinges on its closed-loop design. Energy generated in the secondary coils is partially fed back into the system, creating a self-sustaining cycle that reduces waste. For instance, a portion of the output is routed to recharge the batteries powering the MOSFETs, theoretically enabling continuous operation without external input. This feedback mechanism mirrors concepts explored in early 20th century experiments, particularly those of Nikola Tesla, who demonstrated wireless energy transfer and resonant inductive coupling. Tesla's work with high-frequency alternating currents and air-core transformers laid groundwork that Chikumbutso's design seems to reinterpret for modern applications. Critics often raise questions about energy conservation, arguing that closed-loop systems cannot produce excess power without violating fundamental physical laws. However, proponents counter that the device doesn't create energy but optimizes its reuse. By minimizing losses from heat and resistance, common issues in conventional systems, the technology claims to achieve higher efficiency. Heat management is addressed through an aluminum base that dissipates thermal energy, ensuring stable operation. This aspect is critical, as unchecked heat can degrade components and reduce efficiency over time. To understand the skepticism, it's worth revisiting historical context. For over a century, inventors have sought to harness unconventional energy methods, often met with dismissal due to entrenched industrial interests or scientific dogma. Chikumbutso's work echoes Tesla's struggles, revolutionary ideas initially dismissed as impractical, only to gain recognition decades later. The key distinction here is scalability. While Tesla's wireless power experiments focused on large-scale transmission, this microsonic system targets localized generation, potentially offering decentralized energy solutions for areas with limited grid access. From an engineering perspective, the principles are plausible. High-frequency switching and inductive coupling are well-understood phenomena. Modern power electronics routinely use similar techniques in devices like switch-mode power supplies, which convert energy more efficiently than linear regulators. Where Chikumbutso's design diverges is in its closed-loop configuration and claims of amplifying amperage through frequency manipulation. Independent verification is crucial here. Peer-reviewed testing could determine whether the system's output genuinely exceeds input when accounting for all energy losses, a point of contention in such debates. The broader implications are significant. If validated, this technology could challenge centralized energy models, offering off-grid capabilities for homes, vehicles, or remote infrastructure. It might also reduce reliance on fossil fuels or large-scale renewables, though environmental and economic factors would influence adoption. Yet, practical hurdles remain. Scaling the technology for diverse applications, ensuring durability, and navigating regulatory frameworks are substantial challenges. History is littered with promising prototypes that faltered at commercialization due to unforeseen technical or market barriers. Public reception often hinges on transparency. Chikumbutso's demonstrations, including a claimed electric vehicle powered by his generator, have drawn both intrigue and skepticism. Without open access to technical specifications or third-party testing, doubts persist. This underscores a recurring theme in innovation: the tension between protecting intellectual property and fostering scientific collaboration. For disruptive technologies to gain acceptance, balancing secrecy with verifiable evidence is essential. In evaluating such inventions, it's vital to separate visionary concepts from measurable outcomes. The microsonic energy device represents a fascinating intersection of historical inspiration and modern engineering. Its theoretical foundation aligns with known principles, but practical validation remains the critical next step. Whether it emerges as a transformative breakthrough or a stepping stone for future research, it underscores humanity's relentless drive to innovate. As with all pioneering ideas, time, scrutiny, and adaptability will determine its legacy. For now, it serves as a reminder that the boundaries of science and technology are ever expanding, driven by those willing to question conventions and explore the unknown. The conversation it sparks, about energy independence, sustainable innovation, and the ethics of scientific discovery, is perhaps as valuable as the technology itself.